Hi, in this video, we want to take a look at interaction terms between numeric and binary predictors. Okay, so I want to take us back for a moment. I want us to think about algebraically what happens in a linear model when we have a categorical predictor. Well, what happens ultimately, if we go out and we take our pencil and paper and we work out the details, what it's going to work out as is that for each level of the predictor, of the categorical predictor variable, we end up getting a different y-intercept. Okay, well, that's good. Well, what if we wanted a little bit more? What if we want a different slope for each level of the categorical predictor variable? Or what if we want a different slope and a different y-intercept for the categorical predictor variable? All right, so let's go. I'm going to go skip a little bit lower in the document for a moment, and we're going to take a look. All right. So here, let's take a look at our data. We have a scatter plot. Age is along the x-axis. Amount spent is along the y-axis. And I've colored the points by a categorical variable that's in the data. I've colored it by the categorical variable C. So we can see that C has two levels. And for us, we don't really care what C is. We don't even care what age or amount spent. We just care about the model, right? That's the point of this class. If I'm doing statistics for a specific subject matter, we'll start getting a little bit deeper into what the variables mean. But for us, right now, we're just focused on the math. That's it. Okay, so if I look here, if I just look at the blue, remember all the blue have the same level of the categorical predictor, and all the green have the same level of the other level of the categorical predictor variable. If I look along here, that looks like a line, right? And that looks like a line. Now this is a pretty extreme case. You normally will not see like this distinct of a pattern when there's a difference, but we clearly see a difference. And we can see along this line and this line, they have different y-intercepts and they have different slope very clearly. Okay, so that means that I would somehow want to get a different slope and a different y-intercept depending on which categorical or the value of the categorical predictor variable. Okay, well, we know if we just add on into our equation the categorical predictor, then we're automatically going to get a different y-intercept for each of them. But that's not enough on this, because what that would do, that would give us like railroad tracks. So we would have two parallel lines going parallel with each other through two-dimensional space. What we want non-parallel lines, because clearly these cross. So what we're going to do, we're going to add on an interaction term. And that interaction term, it's going to change the slope depending on the categorical data. And that's how we work with this. Now, when do I want to do this? So if I look at it and I see that my categorical data corresponds to different y-intercepts when I look at the scatter plot, then I know that I just want to add on the categorical predictor in there. I just want to do an addition. Now, if I look and I see two non-parallel lines, so if I see two clearly non-parallel lines, and when I say clearly, remember statistics, we have errors of measurement and stuff like that, statistical variance. So it has to be far enough off from parallel that we will go, yeah, these are not the same slope. And so it's kind of like we do like a visual hypothesis test, honestly. In that situation, I'll add an interaction term. If I see that I have different y-intercept and different slope, then I want to add on the categorical predictor and an interaction term. And that will account for everything. All right, so let's go up and take a look at some stuff. All right, so in R, R will interpret what's going on. It'll figure it out as long as we give it the right information. So here, in the example about to show, amount is the target variable, age is the numeric predictor, and then C is our categorical predictor. So here, if I do amount depends on age, then that's the simplest model possible. What I'm doing is I'm saying that C has no influence on what's going on. Now, if I look at this equation, I have age plus my categorical data What I'm saying is I want a different y-intercept for each level of C. And then I'm going to have, for this one, 2 levels of categories. So therefore, I'm going to have 2 different lines, but they're going to be parallel slopes. They're going to be parallel lines because there's only one coefficient for age. Now, when I get down to these 2, it gets a little bit juicier. So here, when I set this up, this is saying a different y-intercept for the C, for each level C, but this one goes a step further, a different slope for each value of C. And now when I do the star multiplication, what that is saying, says do both of these. So if I want to do different y-intercept, that's just addition. If I want a different slope, I do a colon. If I want both, then what I do, if I do age star C, it will enact all 3 of these for us. And so it's a little bit shorter notation. Might be easier to interpret, might be harder to interpret. If you don't know what the star means, it's definitely harder to interpret, but it's more compact. So, you know, I've yet to see a difference in R for actual implementation. Now, if I want the same y-intercept but a different slope, and this is very rare, that's why I put it last, is I'll put A plus A interaction C. So what we would have is we would have 2 lines coming off of the same y-intercept and then spreading out. This one's very rare. I don't think I've ever seen it in any meaningful work. All right, so let's go ahead and take a look at the data. We've already looked at the scatter plot. Let's look at the actual data itself. So this is the travel data. And something I did just to make things a little bit easier to interpret when I get down to the diagnostic plots, I went ahead and I ordered everything from the columns from right to left. You'll notice I did 4J and number of columns of travel to 1. So it went, I think it's like 4, 3, 2, 1. The columns, I ordered it that way. Hopefully it'll be easier to see if there's any like things popping out on the extreme ends, easier to interpret. And I renamed the row names to go from 1 to the number of rows after I did my ordering. All right, now on this next step, what I did so that I can see which value of my categorical predictor I'm talking about when I look at an individual point, I went ahead and created a color column on my data set, and I used if else. So for if else, what it does, you take a test. So what this is, when it says test, it's a logical statement, true or false. So test has to be equal to something that will be true or false. If it's true, it's going to take on whatever I say yes is. And so I said green. And then, so whenever travel segment is A, I get green. Whenever it's no, I get blue. Okay. All right, so if I go ahead and I call the interaction, so on this part, I want to show you that if I do the call this way with the formula, or if I do the call the full way, I'm going to get the same thing. So here, the formula, I have A star C. Here I have A plus C plus A interact C. So the colon means just interaction, star means addition and interaction. If I go through, I start like looking through these 2 models, I get 1814, 1814. Age is -20 for slope, -20 for slope. -1821, -1821 for the adjustment in the y-intercept. And then the change in slope is 40, change in slope is 40. So it's the same model, doesn't matter how I call it. There might be a difference in some functions, but I've yet to encounter it. I've done some looking. Okay, so let's go ahead and let's build a full model with interaction terms. So all I'm going to do, I'm going to say that my full model, linear model underscore full, is with the full equation, interaction, and addition. And let's just go ahead and build the model. Let's look at the summary function result for it. And we can see the first thing I always look at are the hypothesis tests to see if the coefficients are equal to 0. And clearly, everything is within machine accuracy of 0. Therefore, I conclude that all the coefficients need to be kept, or all the predictor variables should be kept in there. Let's look through. I've got R squared of 0.96, adjusted R squared of almost 0.96. Ooh, all right. So this is looking pretty good. I'm feeling very comfortable with this model. I think that this is pretty good. I'm pretty sure this is fictitious fake data because this is a really good fit. All right, let's go ahead and run Anova. Now, something about Anova is that if I'm looking to get a simpler model to reduce it down, the interaction term is usually what we remove first. So like one school of thought is that if I'm building a model, lower degree polynomials are what I should have before I have higher degree polynomials. All right, so this term is a degree 1 term. It's h to the power of 1. This is a degree 1 term. Like we represent this as just zeros and ones, but it's still a degree 1 term. Now here, I have two variables multiplying. So if you remember multivariable polynomials, which get skipped over a lot in college algebra, I skipped over it as much as I could. You get hit more in like Calc 2 and stuff like that, Calc 3. When you get into multivariable polynomials, the interaction term is actually degree 2. And so the school of thought is if I'm going to have a degree 2 term, all of its lesser degrees have to be kept. Well, this is age and c. Therefore, if I'm going to have an interaction term like this, I have to also have age and I also have to have c. That's a school of thought. In general, you should follow that school of thought. But if you have a good reason not to, you don't have to. You can, go crazy, go rogue, whatever you want. So also, if I had age squared, I would have to keep age in the model under the school of thought. If I had c squared, which wouldn't make sense for this problem, but if I did, I would also have to include c. And remember, if I take the product of two variables, that is a degree 2. If I was to do like h squared interact c, that would be a degree 3 term in my polynomial. Okay, so let's go ahead and make a scatter plot. So amount depends on age. Taking my data, I'm going to color it by that if-else statement. And then I'm going to put down the 2 lines. So here, this is the default y-intercept, and this is the default slope. And if I look down, I get my scatter plot, and I can see that the first line is going very nicely with this. So we can see that we have a y-intercept of a little bit more than 1800, negative slope of close to negative 20. And we can see that's going along with the green. Now, if I look up here, do you remember what the coefficients were? So here was the y-intercept. Now here was c. That was the value of c. I add them together, and I have a new y-intercept, and that's going to be, not too far off from 10, which we can't see the y-axis. And then remember, I had an interaction term. The interaction term was 40.45. If I tack that on to the slope that I had elsewhere, I get this line right here with going along with the blue. And so we can see we really have like 2 different models off of this one data set. Now, why do we do it this way? Well, there is a school of thought based off of degrees of freedom from a statistics point of view that this is a good way to go. And it's based off of a degrees of freedom point of view. And algebraically, this is equivalent to other things. That this is a good way to proceed. It sets it up so that we have fewer hypotheses to test if I'm doing hypothesis testing. If I set up my models in this way, instead of splitting them out. I find it's rather cumbersome to work with at times, but it's up to you, depends on how you want to proceed. It also makes sense when, back in the day when computing power was more scarce, doing things like this weird way that statisticians have set up made more sense. Algebraically, our models will be the same, but our hypotheses testing could be different if we were to like split up the data differently. All right, so let's go ahead and do our box plots. So here, you'll notice that my scatter plot, I've got age along the x-axis and amount spent, but I didn't actually plot amount spent with segments. And we can see that the box plots, from this point of view, the box plots are just about the same. They are as equal as you're going to get. If I was to do a hypothesis test of, a mean of A equals mean of C for amount, the mean of amount given segment equals A and mean of amount given segment equals C, that hypothesis test would surely conclude fail to reject the null hypothesis. So I can't see a difference, but when I look at the scatter plot, oh, it's very obvious. Okay, so now let's go ahead and do a diagnostic plot. Let's take a look at the full model. All right, so remember, I don't want to see a pattern. I'm looking to see, do I see a pattern? If I see a pattern in my residuals, then there's something wrong. Also remember, I sorted the values by amount. So if I see very large values, I know that that's with the more extreme amount values. If I see small values, that's with the lesser values of amount. And these aren't anything too extreme. I don't really see a pattern. It looks like the green and blue version of Fruity Pebbles to me. Now here we have the normal plot. And because of points being on top of each other, it's hard to see if there's anything going on in terms of color, but my feel is that there isn't. I could use transparency on the dots to make this a little bit easier to see. Scale location, I should not see a pattern. I don't see a pattern. Oh, and on the normal plot, I'm also looking at the tails to see if it's deviating from the line. Cook's distance. All right, so number one, we have a bigger Cook's distance at the two extreme ends. That might be something worth checking out. But I'm pretty sure this was fake data. This was generated data, so I'm not going to worry about it. In real life, I would go ahead and take a look at 1 and 925 because those are the most extreme values and they're getting flagged. Now residuals versus leverage, anytime I do a residual plot, I don't want to see a pattern. I don't see a pattern. And also remember that our eyes are really good at finding patterns. So just because you see a pattern, don't be fully convinced. A good rule of thumb is if you can take one dot and move it anywhere or add or subtract a dot from the plot, and if that changes your perception, you don't see a pattern. And Cook's distance versus leverage, and we haven't really talked about these, but we keep on looking at them. Basically, the higher along the contour, the more we want to take a look at it. And once again, we see those two extreme points are coming up. Okay, so now, let's say you're like, no, I don't want interaction. I want to have a simpler model. I don't want to use a categorical variable in there. I want to do a reduced model. I want a simpler model, which is very reasonable because we want the simplest statistical model we can come up with because that's easier for us humans to work with. So what we're going to do, we're going to make a linear model reduced, and I'm just going to remove that categorical variable from my model. That's all I do. Only difference. Let's see what happens. All right, remember previously that all of the variables were statistically significant, right? There was like, woohoo, everything is like super close to zero. Now, by the 0.05 criteria, age is no longer statistically significant. That's just settling. Now let's look at our multiple r squared. We had like 0.96. We had something crazy good. Now I'm 0.003, 0.002. What's going on? And our Anova, if I do Anova just on the reduced model, so here I'm comparing the reduced model to just the average. It concludes that just the sample average is just as good as including age by itself without the categorical predictor. Now, if I run Anova, comparing the full model to the reduced model, it goes, whoa, 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 whoa. There's a difference. There's a difference in these two models. So remember, the null hypothesis, when I compare two models in Anova, the null hypothesis is that they're equally informative. All right, remember, null hypothesis always has an equal sign somewhere. For this, it's equally informative. So kind of a weird equal sign, but think of it that way. They're equally informative. Here, super small p-value. I reject the null hypothesis. I reject the null hypothesis means that they're not equally informative. That means that the more complicated model has more informative value than the simpler model. Therefore, the full model is better than the reduced model. All right, so at this point, we've included the full model is better, but I really want to drive this home. I want to convince you that this is the way to go. So what I'm going to do is I'm going to go ahead and just do the diagnostic plots and show you what's going on. Oh, remember, I do the scatter plot first. This time I put the reduced model regression on the scatter plot, and I can see that it's almost a flat line. I mean, that's practically flat. That means that the slope is for us operationally meaningless. Let's do the diagnostic plots. Do I see a pattern in my residuals? That looks like an X. Yes, I see a pattern. This is bad. I see a pattern in my residual plots. I go, oh no, oh no, oh no. Danger, Dr. Smith, danger. There's a little lost in space reference for you. And here, I can see clearly that the residuals are not normally distributed, but even farther, something you didn't learn from your introductory to stats class, you can see that I've got a bunch of blue over here, I've got a bunch of green over here. It's not just that it's not normal, there's something else going on with these residuals. And it's because of the X pattern. So like we're getting like a lot of info off of this one saying, whoa, 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 time out, time out, time out. This is not the model we want. Scale location. Do I see a pattern? Yes, it looks like a V. And after that, I see a pattern in my colors. So I really see a pattern. And it's not V for victory, it's V for very bad. Now Cook's distance. Cook's distance, whoa, 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 whoa. What is going on here? Like, just stop it. Just stop. Stop. No more plots. No more. Oh, there's another one. Of course. It has to be exceedingly painful for me. This one isn't as bad as I thought it would be, honestly. I thought I was going to cry when I got to this point. All right. Well, that's all I've got for you. I hope you're staying healthy. Take care and goodbye.